Welcome to the Sidense Technical Webinar, 1T-OTP Non-Volatile Memory, a competitive advantage for Power Management ICs. My name is Sean O'Kane from ChipEstimate.com. Today, we are pleased to introduce our speaker, Craig Downing. Mr. Downing is a product manager at Sidense Corporation based in Ottawa, Canada, and he holds a bachelor's in electrical engineering from McGill University. Craig has also worked in the semiconductor industry in various product management and marketing roles for over 15 years. Prior to joining Sidense, Craig held positions with IDT, Tundra Semiconductor, MTech Vision Canada, and Atsana Semiconductor. Please welcome Craig Downing.
Yeah, thanks for the great intro, and thanks to everybody who's calling in today to listen to my presentation. So today I'm going to talk about 20 minutes about non-volatile memory, and in particular how a certain type of NVM, one-time programmable memory, or OTP, can help you design cost-effective, secure and reliable power management ICs, otherwise known as PMICs. I'll start with a few words about Sidense and talk about the semiconductor market and the importance of PMICs. I'll take a look at what PMICs do, implementing programmable features, and how OTP is used to support those features. And we'll conclude with a discussion on how OTP can provide a competitive advantage for PMIC designs. So a few words about Sidense. Sidense develops and sells semiconductor intellectual property. Specifically, Sidense's IP is a type of non-volatile memory, commonly referred to as one-time programmable memory, or OTP. Sidense has been a trusted memory partner since 2004, and financially Sidense is performing very well with a 32% compound annual growth rate in revenue over the previous 4 years. With the backing of stable long-term investors, Sidense is well-resourced with a talented and experienced workforce of over 70, of which over 80% are employed in engineering and R&D roles. Sidense is well regarded for its customer support and provides global support for its offices in North America, Asia, and Europe. We're engaged with over 150 customers worldwide, and we have over 400 design-ins using our technology. And our OTP technology is well proven in many high-volume products and protected by over 120 patents. Let's start by looking at the semiconductor market. The global semiconductor market continues to show growth forecasted in the next few years, from $350.2 billion in 2016, reaching $428.9 billion in 2020, according to a recent IC Insights report. The drivers contributing to this growth are increasing mobile phone production with more complex smartphones rather than simpler feature phones, and an increase in the usage and complexity of automotive electronics, and the rise of the Internet of Things, or the IoT. The IoT has shown a huge growth in the last years with the proliferation of smart sensing devices and more smart connected things. So all of these devices together, the mobile, the IoT, the automotive, we classify as what we call smart connected. And according to recent reports, they represent about 30% of the semiconductor IC market. So the demand for smart connected devices is driving many technological innovations and new developments in the semiconductor industry. These include the introduction of new process technologies and new power-efficient design techniques, such as the use of cost-effective specialty fabrication processes that integrate control logic, analog functions, and robust power stages. So all of this illustrates the importance of power management for smart connected. It is needed to maximize battery life in mobile devices, so they're packing more and more features and high performance with longer use between charges. It's also needed to support more automotive electronic systems and components requiring regulated and control power supplies. And it's also required for managing energy harvesting and very low energy devices for IoT and wearables. Not surprisingly then, the power management chip market represents a significant share of the worldwide semiconductor market. In fact, Transparency Market Research forecasts the overall power management semiconductor market to grow from $40 billion in 2016 to $46 billion in 2019. The power management market comprises a range of devices such as linear regulators, references, voltage supply supervisors, power discretes, power modules, motor controllers, and integrated power management ICs. Out of this, the largest contribution is from those PMICs, whose revenue is forecasted to increase from $11.3 billion in 2015 to $14.7 billion by 2020, according to a recent IC Insights report. So looking at the largest growing segment of mobile devices, which are smartphones, these are packed with features that are supported by powerful application processors. They include multiple sensors, cameras and radios for Wi-Fi, the cellular wireless, of course, Bluetooth, near-field communication radio, GPS, and more. And all this is powered from a single lightweight battery. And that battery needs to deliver end users' expectations of long battery life while using all of those features. So careful management is crucial to providing valuable battery life and a good user experience, and a safe user experience as well, managing that power. So to address this key design requirement, a smartphone typically uses many specialized PMICs. If you look at the main functional blocks in the smartphone mentioned earlier, you can quickly see where the different power management tasks lie. This diagram illustrates with the red blocks where the main power management devices are found in a smartphone alongside the main functional blocks. So all of these main power management blocks are made up with a number of PMICs, in addition to simpler ICs and discrete components. So alongside the battery charger and the main system power management unit are separate PMICs for other tasks and functions. For example, managing power to the display, the camera module, setting the illumination level, and the different radios. Due to the complexity and demands on the power management circuitry, these functions need to be supported by specialized PMICs that control power management at the system level rather than simple on-chip management. So given the number of PMIC devices, the contribution to not only the number of ICs but also to a smartphone's bill of materials cost is quite significant. According to some reports, a typical smartphone design may have $8 worth of PMICs out of a total BOM cost of $42 for the main printed circuit board IC content. That's excluding DRAM and flash memory. Altogether, that's close to 20%. For a tablet, the PMIC cost is even higher, around $20 out of $50 total. So designing to minimize the chip area and the cost of the PMICs will have an important effect on keeping the overall device cost down. So if we look at PMICs in automotive, today's vehicles include increasingly complex and numerous electronic systems for advanced driver assistance, or ADAS, infotainment, engine control, and network connectivity. All of these systems require efficient power management while also addressing them in the face of challenging operating conditions, high operating temperature ranges, long-term reliability, and often unrealistic user expectations, and also government legislated efficiency and safety mandates. In the near to mid-term future, as the car industry moves to autonomous vehicles and electric drive, we can expect even more power management challenges. So if we look at PMICs in the Internet of Things, battery-operated devices for industrial and IoT systems face similar challenges to those of smartphones and automotive electronics, but also have other challenges. For example, the IoT industrial sensors are often located in remote, inaccessible locations where it is not possible to replace the batteries, or they may be in extremely hostile environments, such as an environmental sensor used in oil fields, a temperature sensor at the drill head, for example. Other IoT devices, particularly radio frequency identification RFID devices and wearables, use energy harvesting. So this requires careful management and storage of energy when available, and very careful control of power to save energy during active periods. During these long periods of inactivity, the standby power needs to be minimal, and on activation, the device needs to wake up quickly, do its job, and shut down quickly to save energy. So if we look at the PMIC functions, in summary, there's a wide range of applications, and in summary, power management ICs address one or more of the following areas: programmable system power controllers, battery charging controllers, wireless chargers, energy harvesting, illumination and display control, and also motor control. So if we now take a look at what PMICs do and what is inside them, this slide shows a typical system power management IC. It's taking the elements of more complex PMICs, and these contain several digital and analog functional blocks. There are analog circuits for regulation, sensing and monitoring, with a controller to manage power-up sequencing and PMIC operation overall. The controller circuitry may contain programmable sequencing logic, state machines, or a microcontroller. And shown in the middle of the diagram here is a non-volatile memory block. It's a critical block and is used to store controller code or sequencer configuration settings. And simpler PMICs may use one or more of these functional blocks. For example, a regulator may simply use an OTP to set an output level. Now, the types of NVM that are available to use are one-time programmable memory, embedded flash, multi-time programmable MTP memory, or EEPROM. And we'll talk a bit about the various alternatives later in this presentation. So a multi-purpose programmable power management unit may also have numerous features that can be configured through programming registers and NVM. The regulators and other analog circuits may also employ NVM for saving configuration and trim settings. And all of these functions may be served by a block of NVM containing code and register settings consisting of possibly hundreds of kilobits. Or it could also be implemented using a number of NVM instances around the chip, storing a few bits, say, to set the value of a reference voltage or a scaling factor in different locations. NVM can also be used to save settings to enable features on chip that can be used later by the PMIC supplier to allow a level of customization, or to provide a number of product SKUs from a single die. So looking at the number of features that are found in a PMIC and the kind of things it could do, the list here shows microcontroller code. There's a buck boost output voltage, setting current limits, power and reset delay, standby on off mode settings, power good and fault condition settings, clock timing configuration, and many other things. And as we mentioned briefly, you can also use NVM to turn on and off features to enable various product variants or to customize the design. So as a programmable PMIC has many critical needs for NVM, selecting the appropriate technology is important for chip designers to maximize functionality and performance while minimizing cost. So aside from the function of PMICs and NVM usage, let's quickly look at another important aspect for PMIC manufacturers and designers. That is the semiconductor fabrication processes that are offered by the foundries. Unlike the smartphone's application of baseband processors that are manufactured in leading-edge small geometry processes, many PMICs are fabricated using larger geometries. 180 nanometer is common in current devices, with 130 nanometer and smaller geometries now being deployed. And now, given the importance of PMICs, significant investment has gone into the development of specialized process technologies by the major AAA foundries, IDMs, and specialty foundries. If you look at leading-edge processes in smaller geometries, new 3D structures such as FinFETs pack more transistors and more computationally powerful devices, such as mobile application processors running at higher speeds and lower voltages. Whereas innovation for power applications is provided in processes such as BCD. So BCD integrates bipolar for analog circuitry. It also integrates CMOS logic devices for digital logic, and double diffused DMOS transistors for handling higher voltages and power on the same die. So you add all these together and you get BCD, the BCD process. So some of these processes, in addition to supporting high power and voltage applications, can support junction temperatures of 150 degrees centigrade, 175 or even higher. So these devices can be qualified to support the more demanding automotive requirements that require those temperatures. So semiconductor IP providers likewise can test their IP blocks in these conditions to qualify them to help IC developers get their products through rigorous automotive grade qualification. Another point to mention is that across the various foundries offering BCD processes, many options are available providing logic and I/O devices for operation at 1.8, 3.3, and 5 volt plus various high voltage devices supporting 12 volt, 60 volt, and even higher. Now, for cost-sensitive applications, some processors are offered with 5 volt and high voltage devices only, so this reducing the manufacturing cost by saving the process steps needed for 1.8 volt core devices. So as we talked about, NVM is an important part of PMICs for the reasons previously discussed, and choosing the right technology is important. So let's look at some of the alternatives that are available. So this chart illustrates at a high level the attributes of various embedded NVM technologies that are available for chip designers. On the horizontal axis, we're showing the number of times the memory can be written to or programmed, and this is commonly referred to as endurance. The vertical axis represents the cost of ownership in dollars, and the contributing factors for this are the area of the die and any additional process steps or masks or anything you need to do to bring that technology into a chip. Inside the axis are these various pie charts representing the key NVM attributes, and those are temperature, power, security, and the ability to program in the field. And the bigger the pie slice, the better. Okay, so let's look at the various types, starting with ROM. So mask ROM is permanently programmed during wafer processing, providing an area efficient and fast access memory solution. However, as it's programmed that way, changing the ROM contents involves making a mask change or mask changes, and introducing another fab cycle, introducing additional cost, and probably more importantly, delays in the product availability as you make that change into the die. Embedded flash, eFlash, may be rewritten multiple times and as such is well suited to file storage and other operations where data is constantly being updated, but it too often requires extra processor steps to fabricate. And having said that, flash is available on chip, say for microprocessor design, then this may not be a consideration, but a lack of physical security and limited temperature range support may be an issue for using flash. Another one here is MTP, multi-time programmable memory, and this also allows multiple time programming, but again requires added mass steps, typically with lower endurance than eFlash. The other items there are eFuses. They're available in metal or poly versions and typically supplied by the foundry. eFuses are usually only practical for smaller bit densities and typically require much larger die areas. When you get to the larger capacities, they tend to be impractical compared to other embedded NVM solutions. Finally, OTP, of which are two main types: antifuse, which is the type we'll talk about, supported by Sidense, and floating gate, which uses charge storage. So OTP provides a permanent non-reversible memory that can be programmed once, hence a one-time programmable memory. Antifuse OTP uses an oxide breakdown and typically provides a smaller footprint than the floating gate alternative. Antifuse is also inherently physically secure due to the nature of this oxide breakdown, and it operates over a wide temperature range and can be easily programmed in the field and provides low power operation. Antifuse OTP therefore provides a cost-effective and robust solution for applications we looked at earlier in PMICs. So let's look at this antifuse technology in more detail. One type of antifuse OTP is Sidense's 1T-OTP. Using only a single transistor per bit cell, Sidense's OTP macros consume very little area, and its programming is precisely controlled and permanent. Since programming does not involve charge storage for determining bit cell state like flash does, it is highly secure and consumes little power. No additional mass or process steps are needed to implement Sidense OTP macros, and the design is extremely portable across process nodes and variants. It also operates reliably over a wide temperature range, as wide as -40 to 150 degrees C or even 175 degrees C or higher, making it also suitable for auto-grade applications that need those temperature ranges. So let's have a quick look at the 1T-OTP bit cell, the 1T fuse as shown in the top diagram. The bit cell is formed by a single split channel transistor with thick I/O oxide and thin core oxide regions below the transistor's gate. So applying a sufficiently high programming voltage to the split channel transistor, which is between 5 to 9 volts depending on the process, the thin oxide breaks down, forming a conductive path between the gate and channel. So in doing so, the bit cell is programmed and its state becomes a logic 1, hence the name antifuse, since the fuse is normally blown open. The antifuse is blown closed. Now this programming breakdown location is precise and only occurs in the thin oxide of the channel. It is non-reversible, it's extremely reliable, and results in an easy to read bit cell with a long-term retention of over 10 years at maximum operating temp and with a 100% read duty cycle. Okay, so let's now look at the key OTP solution blocks. This slide shows the typical architecture for a complete 1T OTP solution, which includes 3 main blocks. That is the OTP memory array, which contains all the bit cells, the integrated power supply, which we call the IPS, and a controller block. The memory array consists of multiple bit cells arranged in configurations of varying word size and densities, so they can be grouped together to form banks or sectors for high-speed simultaneous reads and can be designed to provide different trade-offs in that respect. The memory array, in addition to the bit cell, will include sensing amplifiers to detect the bit cell state, multiplexers, decoders, and simple interface control logic. The array circuitry also supports a variety of read modes like single-ended, and differential redundant, which allow the OTP to be optimized for area, power, and security. The integrated power supply, known as the IPS, provides the supply voltages for reading and on-chip programming with a charge pump. If on-chip programming is not required, then an external programming voltage can be applied at test through a pin or a pad on die. So various IPS options are provided to cover a wide range of different use cases given the available power rails that designers have available on their chip. And lastly, the controller provides high-level control of the macros, simplifying the operation and integration into SoC designs. It provides programming control, self-test features, and error detection and correction. So Sidense 1T-OTP is available in several BCD and HV technologies and several foundries. In 180 nanometer BCD, 5-volt only versions of the process are also supported. In these nodes, Sidense boasts a macro area that is actually 2 to 4 times smaller than other NVM solutions, and in some cases can be a much greater difference, say, comparing to eFuses. And the inherent stability and reliability of the Sidense technology over a wide temperature ranges supports applications for automotive power management. Okay. Shown here are two variants of Sidense's SLP-OTP for 180nm BCD processors. At the top is Sidense's SLP-B, which uses the core supply voltage of 1.8 volts and the 5 volt I/O voltage. Below that is the SLP-A, which uses the 5 volt supply only, supporting 5 volt only BCD processors. Both of these are available with optional integrated power supplies that include options to add a charge pump to supply the programming voltage, supporting programming test when field from on-chip suppliers without the need to provide an external power supply for programming. So looking at the advantages these macros can provide for PMIC design, starting with the die area, take for example an NVM requirement for a 256 kilobit macro in 180nm BCD process. In this case, an 8K by 32-bit SLP configuration would be used. In this case, it only has a footprint of only 0.5 millimeters squared, making it very cost-effective for applications requiring code storage and multiple updates of configuration settings, or many different multiple uses for NVM on chip. So this chart here illustrates the potential die cost savings by comparing the estimated cost of this 256K-bit SLP macro to that with an alternative NVM macro that would be using 3 times the area. So in this illustrative example, the potential cost savings per die are approximately 3 cents per die, or approximately 0.3 million for a run of 10 million units. So that's about 10% of the wafer expense. 1T-OTP macros don't require any special mask, process steps, or baking, and this provides further cost advantages. SLP 1T-OTP macros are also available for BCD processors, including 5 volt only, and many of these macros are qualified to support automotive grade qualification for 150°C operation or higher. So delivering these advantages, 1T-OTP is in volume production in a wide range of applications, including mobile and automotive applications with tier 1 manufacturers. So in summary, to meet the demands of smart connected, that's mobile, automotive and IoT electronic systems, PMICs will play an increasingly important role over the next few years as manufacturers strive to produce more competitive and better performing products at competitive costs. Chip designers should consider the selection and use of NVM as a critical part of the design. Out of the various NVM technologies, anti-fuse OTP provides a cost-effective solution for PMIC applications and smart connected devices. In particular, Sidense's split-channel 1T-OTP provides a smaller solution area and hence lower solution cost, while delivering reliable operation over wide temperature ranges. All of this provides potential sources of product differentiation and competitive advantages for your next PMIC design. So thank you very much for attending the webinar today, and thank you for your time.
Okay, Craig, we have a few questions that have come in from our audience. Question number 1. How would you qualify OTP macros for automotive grade?
Yes, good question. So the standards IC manufacturers have to follow to qualify the parts are those given by the Automotive Electronics Council in AEC Q100. As an IP provider, Sidense fabricates the OTP macros on test chips that we take through qualification and characterization for operation over the required temperature ranges, the voltage ranges, and the process variation. We take the parts of the AEC Q100 standards for testing that are applicable to IP, such as the high temperature operating life and high temperature storage, and use that in our testing. So this includes running HTOL and HTS with lots in the oven from -40 to 150 degrees, and some new qualifications up to 175. So this provides our customers with reports that shows the reliable operation of our OTP macros under these conditions, supporting their final device qualification for AEC Q100. That will include the full range of tests applicable to final packaged devices.
Question number 2 is, can 1T-OTP be reprogrammed?
No, the 1T fuse bit cell uses a permanent irreversible breakdown. The bit cell remains stable over a wide range of environmental conditions, running at full duty cycle, that's always on, for over 10 years. 1T-OTP has been proven and manufactured in high volumes in many different process nodes and flavors. However, it can support applications where data or code needs to be updated in the field and during device setup and calibration. So instead of reprogramming, as you would say with Flash or MTP, we emulate MTP, or what we call eMTP. And we do this by providing unprogrammed sections of OTP that can be later programmed with data updates or code patches. So depending on the number and size of the expected updates, the small footprint of 1T-OTP is often better for area. If large files need to be updated many thousands of times, say like a file system, Flash may be better, but for many small setting updates or a few large updates to say update a code patch, eMTP would likely provide a better trade-off in area and hence cost.
Question number 3. What range of process nodes can 1T-OTP support and is larger than 180 nanometer supported?
1T-OTP has been proven in 180 nanometer all the way to 16 nanometer in silicon. So for geometries 180 nanometer and smaller, the advantages of using 1T-OTP antifuse become more pronounced. And at larger geometries, the breakdown voltage to program voltage gets higher and is less practical. At the other end of the scale, 1T-OTP can support smaller geometries than 16 nanometer.
And our final question, what are the configurations and bus widths that the SLP macros support?
So SLP macros for BCD and general purpose logic support a range of 256 bits to 256 kilobits. And they have I/O widths that include by 8, by 16, and by 32 bits. As do other Sidense OTP macros, they also support a few different read modes in addition to single-ended mode that uses 1 bit cell per logical bit. They include a redundant mode, a differential mode using complementary bits, and a combination differential redundant mode that uses both. These all improve read margins and support reading at lower and lower voltages. The differential mode also provides better security for such things as key storage, as the complementary scheme cancels out power signatures, foiling methods for hacking using power analysis.
Thank you for joining us today to learn more about Sidense 1T-OTP Non-Volatile Memory, a competitive advantage for Power Management ICs. For more information about 1T-OTP Non-Volatile Memory, visit Sidense.com.